Did you solve the problem, ma? No one has solved it. See, what have this is not correct, ma, because in heat transfer, there will be so many number of problems. You cannot expect me to solve each and every problem, ma. Anyway, I will be giving you assignment next week. I will be giving you assignment, and I will give you at least 4 or 5 problems for you people to practice. So, so it will be easier for you to if you practice the problems. Is it visible? The slide is visible.
Yes, sir.
Yes, sir.
Yes,
This is
sir.
this is the problem I gave you last class, right? And I have uploaded this in the what's that the PPT in MS Teams also. Mo, have you seen it?
Yes, sir.
Okay, ma. So this is the problem. Yeah, no one has solved it. Tambi? Oh, you people, brothers, did did you solve it or not? No one has solved it, huh?
No, sir. But we'll solve now.
You want me to solve, or shall you solve it?
Anything, sir. You can.
Okay. So let us see. This is the diagram which is given. Is it visible to you all?
Yes, sir.
Yes, sir.
Okay. So the area given here is 0.1 meter squared. Okay, and this is a composite wall. Okay, and here you can see here. So the especially when you talk about the middle layer, right? The middle layer actually it is 50%. Now the flow area is also, it will be 0.05 meter squared for B and 0.05 meter squared for D. Is it okay?
Yes, sir.
Because the total area is mentioned as 0.1 meter squared. Is it fine?
Yes, sir.
Yes, sir.
I am talking about the middle layer, B and D. Okay, remaining other for A and C, the area will be 0.1 meter squared only. Is it okay, ma? Everyone?
Yes, sir.
Yes, sir.
Okay, ma. Now, first, let us, what are the things which is asked in the question? Find the heat transfer per unit area. Okay, so Q is the one which is asked, right? So, we know that Q which is equal to, let this be T1, T2, T3 and T4. Okay, T1 minus T4. Okay, let this be T4 divided by all the resistances. Am I correct? Am I
Yes, sir.
correct, students? Am I correct or not?
Yes, sir.
Yes, sir.
Okay, so Q equal to T1 minus T4 divided by R suffix A plus R suffix BD plus R suffix C. Is it correct?
Yes.
Yes, sir.
Okay. Now, first I want to find out what is the resistance R suffix A. R suffix A will be equal to L suffix A divided by K suffix A into A suffix A. Am I correct? L by Ka.
Yes, sir.
So, what is the thickness of A? It is mentioned as 2.5 centimeter. Am I correct?
Yes, sir.
So, you have to substitute in meters. 2.5 into 10 power minus 2. 0.025.
Yes, sir.
See, please correct me if I do it wrongly. Okay, because you people, you are experts than me when it comes to mathematics. And Ka is mentioned as 150, right? 150 into 0.1. So how much the resistance?
Sir, 1.66 into
1
10 power minus 3.
1.66 into 10 power minus 3.
Yeah.
What is the unit, ma?
WK inverse. W by K.
W by K. Is it correct? Because length will be in meters and thermal conductivity is watt per meter degree C or Kelvin, and area is in meter squared. Okay, so meter, and then meter. So it will be Kelvin by watt, right? Or degree C by watt. Am I correct or not?
Yes, sir.
Yes, sir.
So Kelvin by watt. Okay, now I have found out the first one, and similarly RC is also easier. So R suffix C, L suffix C divided by K suffix C into A suffix C. So again, what is the thickness here? The thickness is
0.05.
5 centimeter. So substituting it in meters. See, students usually the students do the mistake here. Okay, so 5 centimeter now immediately write 5 into 10 power minus 2. The calculator will take care of all these things. Instead of putting 0.05, somebody they will since they want to do the problem at a faster rate, they will put 0.5. Generally, this is what happens when I correct the answer papers, especially e-transfer subjects. Okay, because I am handling this particular subject at least the 6th or 7th time in my career. Okay, so generally the students they used to do this, and similarly there is the thermal conductivity. So the thermal conductivity of each and every layer varies. Okay, K suffix C is 50, right? 50 watt per meter Kelvin. So 50 into area again 0.1. So how much it is?
0.01 K by W.
0.01. Is it correct?
Yes, sir. 0.01.
Kelvin by watt. Okay. Now we have here parallel circuit here, B and D. Actually, the circuit will be more or like this. Okay. So when we draw the thermal circuit, so the circuit for this particular diagram for a particular problem is the circuit for this particular problem is, it will be like this. So you have T1 and resistance offered by A, and then this is T2, this is T3, T4. Am I correct, ma?
Uh,
Am I correct? Is this the circuit?
Yes, sir.
All of you are able to understand this, the thermal circuit by using electrical analogy. When we do that for this particular composite wall, it will be like this. Am I correct?
yes, sir.
Now we have found out what RA we have found out, RC we have found out. Now we have to find out RBD, right? So RB suffix D we have to find out. We know that in case of parallel circuit, 1 by RBD will be equal to 1 by RB plus 1 by R suffix D. Okay, so 1 by RBD will be equal to RB plus RD divided by RB. Am I correct?
Yes, sir.
Yes, sir.
Which implies RBD will be equal to RD divided by RB plus RD. Okay. Am I correct or not?
Correct, sir.
Please correct me if I am wrong. Now, taking this R suffix B. R suffix B is LB by A suffix B into A suffix B. So we will be having LB 7.5 and K suffix B is 30. A suffix B is 0.05. It is not 0.1. It is 50% of the area. Okay. So 30 into 0.05, 7.5, right? So 7.5 divided by, sorry, into 10 power minus 2. This is what happens. Even I do the mistake here, right? So substituting it meters. Okay, so that's very important. Okay, even that's what I normally people students will be doing this mistakes. 30 into 0.05. So this is the first one, R suffix B. Similarly, R suffix C, sorry, not R suffix C, R suffix D, resistance for D is again 7.5 into 10 power minus 2 divided by the thermal conductivity of D is 70. 70 into 0.05. So what is this values? RB
Sir,
and R
RB is coming as 0.05.
0.05.
And RD is coming as 0.02143.
Is it fine, students? All of you please check.
Yes, sir. I'm getting the same values.
0.05 and 0.0214.
Yes, sir.
Okay, ma. Now, finally, the answer. When you talk about the final answer is, yeah. Now, yeah. One more thing which I missed out. We have got RB/RD. Now, I have to get RBD. So we know that now substitute here in this.
So we get 0.014.
So,
Actually, we can round to 0.015.
RBD will be equal to, I am writing the step here. RBD, which is equal to RB into RD, that is 0.05 into 0.0214. 0.05 into 0.0214 divided by the sum of these two. Am I correct?
Yes, sir.
So how much it comes, ma?
Sir, approximately
Round to
0.015.
0.015.
0.015. Again, the unit is Kelvin by watt. Am I correct?
Yes, sir.
So finally, the heat transferred. Finally, the heat transferred is Q, which is equal to del T divided by sigma R. So temperature differences, we know that it is 370 minus 66. See, when you substitute in Kelvin or degree C, the temperature difference remains the same. I have already told you 100 degrees minus 0 degrees is 100. 373 Kelvin minus 273 Kelvin is equal to 100. The del T remains the same. Is it fine, students?
Yes, sir.
So now substitute this RA, RB and sorry, RA, RC and
RBD.
RBD. 1.66 into 10 power minus 3, 0.01 and so I let me rewrite it here. What is RBD we got, ma? In the previous slide?
0.015.
0.015. And the last one, R suffix C?
0.01.
Is it? Yeah, it is 0.01. Now tell me the answer. Heat transfer. What is the answer, ma? Hello? Are you there? Am I audible?
Yes, sir. Yes, sir.
Ah,
Calculating.
11,385.7.
11,385.7
0.76.
watts. Okay,
Yes.
11,385.7 watts. So this is the final answer. That is correct. That is correct. Okay, so when we talk about composite wall, we can solve like this. All of you have taken this?
Yes, sir.
Yes, sir.
Everyone? See, some of the students, they think
Yes.
that I will
Sir.
just go through the videos. Please don't do that. Please solve the problem then and there, because assignment I will give you more problem. During that time, you have to refer the class notes and then you have to solve. Okay, shall I move on?
Yes, sir.
Okay, ma. So when we talk about composite wall, we have this. Okay, now before going on to composite cylinders, okay, before moving on to composite cylinder, yeah, this is the series parallel composite wall which we have discussed. Okay, now when you talk about the see, even in this previous problem, right, you can see here that is one wall of different thermal conductivity is attached to another wall with a different thermal conductivity. Okay, so very good example is furnace wall, right? Very good example is furnace wall. Okay, when we talk about the furnace wall, what happens is if the furnace wall, that is the one layer and the other layer, if it is not pasted properly, right, and if you have air gaps or if you have gaps like this, then what happens is this, the resistance reduces abruptly. Okay, the resistance reduces abruptly, or contact resistance is primarily due to surface roughness effect because gaps are filled with fluid. Okay, so what happens here is, you can see here metal interface, that is aluminum interface under vacuum, you can see the resistance. Whereas when we have air, you can look into the resistance, and when you have silicone and aluminum, you can look into the resistance. Okay, so the resistance values vary, right? It vary depends upon the gap. Okay, so you may think that I have connected two metals. Okay, I'm doing a, see, so for example, assuming yourself as that is working in a R&D in a refrigerator company or air conditioning company, right? So you may think that, so I have done well. I made the composite wall really well. Okay, with the air gap in it. Okay, but the distance of the air gap, or the thickness of the air gap is also very important. The vacuum, the distance between the two layers is also very important. Okay, so the resistance varies, okay, depending upon the air gap and depending upon the fluid also, right? And I have already told you, see, this concept is usually applicable in case of composite wall, we apply it to refrigerator walls, and similarly we apply it to furnace walls, right? Whereas in case of composite cylinders, we apply it to steam pipe. Okay, nuclear reactor, thermal power plant, nuclear power plant, and all. We will be applying this particular concept there. Is it fine, students? Students, all of you are
Yes, sir.
able to understand what I say? If there is some gap, then naturally the resistance varies. Is it fine?
Yes, sir.
Hello?
Yes,
Am I
sir.
audible?
Yes, sir, you're audible, sir.
See, there is no response at all. Yeah. See, heat transfer is an important subject, ma. It's not only about numericals alone. It's the concept which is very important. Okay, because see, don't think that I will be asking you only problems in the CAT exams or FAT exams. Okay, a small theory will be associated with it, and if you don't explain it properly, You may think that I solved the problem correctly, but you won't get 10 marks. Please understand that. Now, I'm saying don't come and fight with me after CAT exams or FAT exams. Okay, and when we talk about cylinders, similarly, when we talk about cylinders, okay, we know that the very good example is the steam pipe. Okay, the steam pipe usually it is insulated with insulator material. Okay, the steam pipe will be having thickness. The inner radius will be R1 and the outer radius will be R2, and then it is covered with some layers of insulation that may be regarded as R3. Okay, so the thickness will be R2 minus R3 will give you the thickness. Okay, now what about the heat transferred? Okay, in case of a pipe which carries, or in case of a cylinder, usually steam pipe is assumed as a hot pipe which carries hot fluid. Okay, and the cold fluid is nothing but the surrounding atmospheric temperature. Now, how you get this expression? Anyone of you can you say this? How you get this expression? Heat. See, what are the three resistances? First, tell me. What is the first resistance? What is the second resistance? And what is the third resistance? Can anyone tell?
So the first and the third one is convective resistance, sir.
Very
And the
good. The first and the third one is convective resistance, which depends upon the convective heat transfer coefficient of the hot fluid and the convective heat transfer coefficient of the cold fluid. And second resistance is
conductive resistance.
conductive resistance. It depends upon the thermal conductivity of the pipe material. It depends upon the thermal conductivity of the pipe material. See how you got this. Let me explain you briefly. Shall I rub this off?
Yes, sir.
Yes, sir.
Now, assume, don't assume hot fluid and cold fluid. Just assume that the cylinder one minute, ma. 1 minute. I'm sorry. The next the house construction work is going on, so the drilling it affects me. That's why. Okay. So now you have this. All of you are able to see this.
Yes, sir.
Yes, sir.
Okay. So assume that the inner surface is hot, which is at a temperature T1, and outer surface is cold, which is at a temperature T2, and let K be the thermal conductivity. Now, when you take a circular tube like this, okay, when the fluid will be flowing inside. Am I correct? Am I correct or not?
Yes, sir.
So, and the heat transferred is usually the surface area. Am I correct?
Yes, sir.
Okay, and let L be the length of the tube. Is it fine?
Yes.
Okay, so the heat is transferred to the surface. Okay, so the fluid will be, so the sectional area will be pi d squared by 4 or pi r squared, whereas the surface area is pi dl. Am I correct?
Yes, sir.
Okay, now we know that Q, which is equal to minus Ka dt divided by dr here. Okay, because the radius varies. So this is R1. So this is R1 and this is R2. The inner radius is R1 and outer radius is R2. Is it fine, students? Is it fine? Is it
Yes, sir.
fine or not? Now QdR, which is equal to minus Ka dt. I can rewrite like this. Am I correct?
Yes, sir.
So inner temperature is T1 and outer temperature is T2 and the thermal conductivity is K. Is it fine? Is it fine or not?
Fine, sir.
Now Q dr, integrating dr, R1, R2 being the limits and minus K into A into integral dt, T1 and T2 be the upper and lower limits. Is it fine?
Fine, sir.
Now Q into dr. Now R1, R2 dr, which is equal to minus K into A into 2 pi RL. Am I correct? Pi dl or 2 pi RL, the surface area.
Correct, sir.
Okay. Integral dt, T1 and T2. Now, taking this 2 pi RL to the other side, Q into dr by R into 2 pi L. Am I correct?
Correct, sir.
Okay, this 2 pi L, I have the liberty to take it outside. Is it correct?
Correct, sir.
Okay. Now, Q by 2 pi L.
Sir?
Yeah.
So how is it dt by t, sir? Shouldn't it just be dt?
I'm sorry. DT. It's not dt by t. It's dt alone. I am sorry. I'm sorry. dt alone, ma. That's correct. That's correct. So now what happens? Q by 2 pi L into dr by R and substituting the upper limits R1 and R2, lower and upper limits. So this takes this form. This is the final form, right? Is it fine, students?
Yes, sir.
Is it fine? What I written? Please wait a minute. Hello. Am I audible, ma?
Yes, sir.
Audible, sir.
Yeah. Now substituting this Q by 2 pi L into dr by R. 1 by R dr is nothing but natural log of R. Am I correct? Am I correct or not?
Yes, sir.
And minus K into dt is T. Upper temperature, upper limit is T2, lower is T1. So now what happens here is this I rewrite it as Q by 2 pi L natural log of R2 minus R1. R2 minus R1 becomes, I can rewrite natural log of R2 by R1. Am I correct?
Yes, sir.
One step I
Yes, sir.
skipped. Natural log of R2 minus natural log of R1 it will come. Natural log of R2 minus R1 is natural log of R2 divided by R1. Am I correct?
Yes, sir.
Okay. Which is equal to minus K into T2 minus T1. When this minus sign enters inside, it becomes K into T1 minus T2. Is it fine?
Yes, sir.
So finally, this expression becomes Q, which is equal to, when I take all the terms to the other side, Q which is equal to K into 2 pi KL. Am I correct? Yeah. 2 pi KL divided by is it 2 pi KL, ma? Yeah. Where L is nothing but the length of the tube. into T1 minus T2 divided by natural log of. Is it fine, students?
Yes, sir.
Yes, sir.
This I can rewrite it as T1 minus T2 divided by natural log of R2 by R1 divided by 2 pi KL. This is nothing but the resistance offered by the surface or the metal due to the thermal conductivity. Natural log of R2 by R1 divided by 2 pi KL. Is it fine? Is it fine, ma?
Yes, sir.
This is good, sir.
Which is equal to del T divided by R thermal resistance. Conductivity resistance. I'm sorry. R conductive. Is it fine? All of you understand
Fine,
this, how
sir.
I got this? What I did is Q equal to dt by dr, Q equal to minus Ka.
Sir, can you scroll down?
Yeah, Q equal to minus Ka dt by dr, Q dr equal to minus Ka dt. So when I substitute, when I integrate dr with the limits r1 and r2 and t1 and t2 on the right hand side, I get the expression Q dr by r. When I substitute area as 2 pi RL, okay, that R comes to the other side. Okay, R by 2 pi L, R into 2 pi L comes to the other side. So 2 pi L is a constant. I am taking the 2 pi L outside. So what happens to this is integral dr by r. Now upper limit is r2 and lower limit is r1. And similarly on the other side also we have integral dt, t2 and t1 being the upper and lower limits into minus k. So when I substitute it, you will be getting natural log of r. 1 by r dr is natural log of r, and when you substitute the upper and lower limits r2 and r1, it becomes natural log of r2 minus natural log of r1. We know that natural log of r2 minus natural log of r1, we can rewrite it as q into 2 pi l divided into natural log of r2 divided by r1, which is equal to minus k into t2 minus t1. When the minus sign enters inside, it becomes k into t1 minus t2. And finally what happens is uh, when the 2 pi k, when it goes to the other side, it becomes 2 pi kl into del t divided by natural log of r2 by r1. So which is equal to t1 minus t2 divided by natural log of r2 divided by r1 divided by 2 pi kl. Okay, so which is nothing but del t divided by thermal conductivity resistance or conductivity. Is it fine? Is it fine, ma?
Fine, sir.
Is it?
Yes, sir.
This is what it was mentioned here. Natural log of R2 by R1 divided by 2 pi KL. Did you got this? How this resistance comes? Is
Yes,
it
sir.
fine?
Okay.
Natural log of R2 divided by R1 divided by 2 pi KL. I have written here. It was mentioned here. Am I correct?
Yes, sir.
See, one more thing here. I am not a max teacher. I am a heat transfer professor. Okay. So you have to excuse me. So you have to do the small mathematical integration as well as differentiation in this heat transfer subject. Okay, and when we involve the hot fluid and cold fluid, then what happens here is you will be having H as the hot fluid thermal conductivity. I'm sorry, hot fluid heat transfer coefficient, convective heat transfer coefficient, and T infinity 1 is nothing but the hot fluid temperature, and cold fluid heat transfer coefficient is convective heat transfer coefficient is H2, and T infinity 2 is nothing but the cold fluid temperature. Okay, and thermal conductivity of the substance is K. Okay, pipe material, and inner radius is R1 and outer radius is R2. So in case of cylinders, we will be having this. Is it fine? Is it fine,
Yes,
ma?
sir.
Okay. So
Yes.
when we try to do all these things, okay, whatever expression I got, there are certain assumptions. Okay, one, we used to assume it is a hollow cylinder, steady state condition, no internal heat generation, constant thermal conductivity. All these things I told you when we uh, when we did the expression for heat conducted in a composite wall. Okay, so one is there should not be no internal heat generation. I showed you the value. Sorry, I showed you the equation. Am I correct? The Cartesian coordinate equation. Okay, so this is the Cartesian coordinate equation. What all the terms become zero here? Can anyone tell me? What are all the terms which become zero here? I'm talking about this equation.
Sir, if it's a steady state equation, then the right hand side becomes zero, sir.
Yeah, very good. The right hand side becomes zero. What happens to G by K? Internal heat generation. If there is no internal heat
If there is
generation,
no internal heat generation, that term becomes zero.
G by K becomes zero. What happens to dou square T by dou Y square and dou Z square?
One dimensional.
When it's a
One
one-dimensional
dimensional.
case.
Yeah.
Only, sir.
So what are all the assumptions? We assume one dimensional thing. We assume there is no internal heat generation, and we assume steady state condition. Okay, all the three things we assume. Okay, so the same thing. So now what happens here is the whole equation becomes dou square T by dou X squared, which is equal to zero. And when we get the solution, we get T of X, which is equal to C1X plus C2. Okay, so this is the first case. Similarly here also, that is for composite wall. In case of composite cylinder, the basic assumption is we have to assume steady state condition, no heat generation, and the final one, constant thermal conductivity in all the three directions. I have told you this particular point in the very first class. See, you have to relate all those things. See, in the expression, we stated kx, ky, kz, right? We have stated kx, ky, kz, although it is missing in the one more thing which I have shown you. I have told you kx, ky, and kz, and the thermal conductivity in all the three directions. Okay, for material, isotropic material. Okay, so the thermal conductivity in all the three directions is assumed to be a constant, or k equal to constant. Okay, k equal to constant. Then naturally what happens is we will be getting this expression. Okay, so that particular thing also you should know. Okay, you should know. So, and similarly, when you have a composite cylinder with so many layers of insulation, okay, for example, you will be having the pipe material. R1 and R2 may be the inner radius and R2 may be the outer radius, and then you will be having two insulation like R3 and R4 were nothing but the radius of insulation, two insulations, and you will be having inner fluid and you will be having outer fluid. The inner fluid may be hot steam and the outer fluid may be cold fluid. Okay, so in that case the resistance will be like this. Okay, so you will be having convective resistance and offered by the fluid inside, and then you will be having conductive resistance offered by the pipe material, first insulator, second insulator, and again convective resistance offered by the cold fluid. Is it fine? Is it fine?
Fine, sir.
And one more important thing, when you write 1 by HA, we know that 1 by HA, the area pi dl, we know that, or 2 pi RL. So when we talk about the inner surface, when you talk about the hot fluid is acting on the inner radius, 2 pi R1L, and the cold fluid is acting on the outer surface. So it should be 2 pi R4 into L. This particular point is very, very important. Some of the students, they used to do the mistake here. Okay, see, these are all small things the student does mistake. Okay, so instead of substituting 2 pi R1 into L, they will be substituting some other thing. And here also, instead of substituting 2 pi R4 into L, why R4 is considered? Because the outer radius is exposed to the cold fluid. Am I correct?
Yes, sir.
Correct, ma. I'm shouting like anything and you people are not.
Yes, sir. Yes, sir.
See, I'm not that, see, my health is not that much great. And the inner fluid is exposed to hot fluid. Okay, so the radius is 2 pi R1 into L, or the area. Radius is R1 and the area is, surface area is pi dl, or 2 pi R1 into L. Is it fine, students? Is it fine?
Yes, sir.
Fine,
Yes, sir.
Yes, sir.
Any doubt in this?
No, sir.
Okay. So the critical thickness of insulation, I will do it after I will solve one problem. Uh, You can take down the third problem. This third problem, I will just solve this, and then I will go to the concept of critical radius of insulation. When the class ends by 11:45, right?
35, sir.
11:35.
Yes, sir. 35.
Oh. Okay, all of you try to solve this problem number 3. Okay. The inner dia of the pipe is 10 centimeter. Wall thickness is 1 centimeter. Thickness of insulation is 3 centimeter. So critical radius of insulation is not asked here. Okay, so you can try to solve this problem. Okay, tomorrow I will if you are not able to do it, I will solve it tomorrow. Is it fine?
Okay, sir.
Is it fine,
Okay, sir.
students?
Yes, sir.
Yes,
Okay,
sir.
sir.
I thought I will be having time up to 11:45. See.